There are many different optimization problems we can do from reaction kinetics. One of them happens to be a series reaction. A goes to B, goes to C, with rate constant K1 and K2. Right? Have you already done this problem in reaction kinetics?
Yes.
Okay. No?
It depends where you're going.
Okay, well I think even if you have done it, I will do it again because I will show you a different way of solving a differential equation. I think you most likely solve differential equations and reaction kinetics by using integrating factor. I'll just show you a different way of doing it, which I think is always nicer. So let's say you have a batch reactor. Okay? A batch reactor going on, which means you mix A, B, and C, whatever ratios you want. But right now, for simplicity, let's start assuming that you mix purine. You just put purine, okay? And let's say that B is your desired product. Okay? Now, if you run the reaction for infinite time, what's going to happen? You'll only have C, right? So, our goal is to maximize the production of B. Now, I could make the problem a little bit more complicated, say, it's not that we're going to maximize the cost of B. We can optimize some different combinations. So I can put more constraints into the problem, more economic constraints. But right now, I don't want to start that. I want to start with the simplest problem, which is maximize the concentration of B. So you start with simple mass balances, which simply is dCA dt is minus K1 Ca dCB dt is what?
Plus K1A.
K1Ca
Minus
K2Cb, and of course dCc dt is K2Cb, right? So it's not that difficult to actually solve these differential equations. In fact, the first one is obviously trivial. You solve this and what do you get?
CA equals CA naught e to the negative 1.
Right? I'm not even going to do it. I'm sure you all are capable of doing that. All right, that's good. So now, of course, you can plug that into the second equation. So this equation becomes right? All right, that's still actually a fairly easy differential equation to solve. But how would you go about solving that?
I think you put it on the
Yeah.
left.
I would let the right side be a linear term. You see what I'm saying? No.
You put the
The whole left
CVs
part.
on the left side.
Okay, yeah. You go ahead and solve it.
Yeah.
You can either do an integrating factor, what I'm guessing what you're going to do is you can make kind of a substitution and say that
It's a substitution.
No, you got, so yeah, I always, if you guys have taken transport with me, you always know what I say, right? Say if you want to solve a differential equation, first tell me what kind of differential equation it is.
Oh, right
you
here.
know that, you always can solve it.
That's how you solve it. Right here. Right there. Boom. That's my cheat sheet for kinetics.
Yeah, that's the integrating factor.
Yeah. Boom.
Cheat sheet, again, what cheat sheet? You guys are just bored with these cheat sheets. Stop thinking, that's another example. The cheat sheet, don't think, oh, okay, got it. Solve it.
I love it.
It wasn't what? It wasn't helpful. It didn't help. Good. You know why it didn't help? Because you had it. If you didn't have it, you were being perfect. You were relying on it. No. That's a mistake everybody makes. You rely on cheat sheet.
After 15 minutes, I said on the ground.
You sat on the ground?
Yeah, I'm just like.
For the cheat sheet, you mean?
Yeah.
Oh, good.
After we read the test.
What?
Set it on the
All right. Shh, let's come back here. So I always, if you remember, I say, okay, talk about this differential equation to me. So you start with, what is the most important property of a differential equation? What's the most important thing? Order is important, but really linear versus non-linear is really the most important thing, because if it's non-linear, you have no hope of solving it. So your only hope, and you'll only get linear equations to solve your curriculum, so you'll only see linear. But this equation is linear or non-linear? Well, I already told you you'll only get linear, so always is linear. But some people get confused by this term. Why is it? Is this term linear or non-linear?
Linear and expected.
Is linear?
It's non-linear.
So then why is this equation, differential equation, a linear differential equation? It's
linear.
linear in the unknown. That's a nonlinear term in time, but time is known. So we are solving for CB. CB is unknown. So anything involving time doesn't bother us. It's anything involving CB or CSCC. CS, CB, CC are the three unknowns. If you have any nonlinear of these three, we are in trouble. But here, fortunately, you can see CA linear, 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 linear. So everything is linear. And so obviously this equation is also linear. Second thing is ordinary versus partial. What is this, ordinary or partial? It's obviously ordinary differential equation. Second is order. To find what is the order of this equation? First order. The last thing is homogeneous or non-homogeneous. What is this? Non-homogeneous. So why is it non-homogeneous? Non-homogeneous because if you put CB equals to 0, this equation is not satisfied. So if it's a non-homogeneous equation, you can split it into a homogeneous solution and a particular solution. I think, is that what you're trying to say? Okay. So then it's actually, once you have that idea in mind, it actually becomes very easy to solve. Integrating factor is not difficult either. For integrating factor, you kind of have to think a little bit more. So you say, okay, the homogeneous part is trivial. The homogeneous part is trivial because you throw this away. So you already know the solution because that's basically there, right? So you know the CB is the homogeneous part, let's say some constant e to the power minus k2t, right? Make sense? That's a homogeneous solution because that comes about by throwing this away, plus a particular solution. Now how do you figure out particular solutions of equations, differential equations? Well, they have initial condition, but you still got to first figure out the particular solution. Initial condition will help you figure out the constants. Now, how do you figure out the particular solution? It's a very nice approach. What is it? You just look and decide. The particular solution looks like the non-homogeneity. So it's basically a trial approach or whatever you want to call it. But if this is the non-homogeneity, so particular solution will also look like this, exponentials. So you try a particular solution of form beta e to the power minus k1t. So you try that. You plug it in. If you plug it in, what's the derivative? You get dCb dt. What is the derivative of this? Minus k1 beta, right? Right, times the exponential. But exponential will just cancel. Equals to k1 ca0 minus k2 times cb, and cb is beta. From this you get beta to be simply k1 ca0 divided by k2 minus k1. Hence your solution. And you also know at time t equal to 0, the concentration Cb must be 0, so this must be a negative term. There must be a minus here. Right? Well, actually, let me just do it step by step, not too fast. So you know that beta, so therefore this will be equal to k1 ca0 divided by k2 minus k1, right? E to power minus k1t, and then because of the initial condition, minus e to power minus k1. This is Cb. Is it easier than is it easier than integrating factor or not? No? Alright, I guess to each his own. I think it has a little bit more physics into it, so I find it easy, always more compelling. Alright, but anyway, I don't care which way you get it, so let's say your expression is Cb. So now how are you going to figure out the time at which the concentration of Cb is maximum? Or concentration of B is maximum?
Derive it with respect
Sorry?
to time.
Yeah, just take derivative with respect to time, so it equal to 0. And then if you really want, you can take second derivative also. But in most of these cases, usually physics tells you there's only one answer, it is the maximum or minimum. Like in this case, you know that. You know as t goes to infinity, Cb will go to 0. Right, as t goes to 0, you know Cb is 0. So you know if there's only one optima, it has to be a maximum. Right? So therefore, you just take the derivative that equal to 0 and you can solve for it. So you said dCV dt 0. This stuff outside doesn't really matter, right? Because it's just a constant. So you get minus k1 t log, oh sorry, minus k1 e to the power minus k1 t plus k2 e to the power minus k2 t equals to 0, right? So therefore you will get I guess I can remove this minus, put it equal to here, right? And therefore you get each power minus k1t divided e to the power minus k2t equals to k2 over k1.
How do we get to this? What were we talking about before?
Sorry?
What were we talking about before? How do we get to kinetics?
We are trying to optimize. I'm telling you that they're different because to design, to figure out how to make most money on a plant, right? First we figured out, but when designing that, we talked about the cost of the reactors, cost about heat exchangers, cost a bunch of those things, right? We just said those are known numbers. But now we are realizing that that's not quite true. There are a lot of reasons why those are not perfectly known numbers. Some of it could be uncertainty. Another thing is each of that equipment needs to be optimally designed so that you actually make most money. So if you really want to make most money, the first thing you have to do is you have to design each and every